underscore TW.
Yeah.
EAN underscore
TW. Yeah.
Yeah.
Still doesn't work.
Aha. Here's Jeff.
Read actually.
So yeah, I use for financial.
Sure.
You know,
It's not usually at the top of like use cases, I guess, from what I've seen. So you can see more of the small ones with like images.
Whoa.
I don't know. Yeah.
What do I see?
Right.
All right, I sent you the link, and we're live.
Okay. Okay, let's get started. Set it down.
Right, I don't want this. I want this.
So this is my name. So
An idea could be,
Should I start? Or,
still clear. So how can I use my? I just set out a new data science experience.
how many more?
Just set out a new one.
Are you doing the CNN next? Okay. And is this model complete or just close to complete?
there's a few more points here. Basically, sort of looking at dropout.
Okay, so I can use the Chrome.
Can we do that at the break? Just so that we kind of start. That way, everyone will actually spend some time like 4 o'clock to kind of, in the room to just work through the DSX and download, upload, and all that stuff. So it's kind of ready to go.
Yep. Okay, so let's continue. Remember where we were, right? We're trying to classify letters, images. We built a toy little model. Where was our model? Here's our model, right? With one hidden layer, 128 units, so they can learn 128 different features of your images, and then we're going to combine those into 10 probabilities in the output. And then we trained it for a while, and we saw that it was overfitting, right? So we're getting better and better accuracy, almost 95% here after 20 epochs on the training data, but it's not doing any better on validation really after like 5 or 6 epochs. In fact, it's actually getting worse. So yeah, that's bad. So what are we going to do? Bigger model. To try to capture more of the real variety. And so here what I'm doing is I'm adding two hidden layers now. I'm making them bigger. So instead of 128 units, I made 512. It's converting 4 times as many things at the first level, still have activation function. Now I'm also adding dropout, right? So what this is saying is the probability 20% for every input element, just get rid of all the edges, not all of it, each individual edge independently, with probability 20%. And so what that means is, hopefully it's going to encourage the network to learn more general representations and sort of say, look, if enough of these things all point to this being an A, say A, as opposed to saying, if pixel 344 is black, then say A. The latter is much more likely to be, memorization of the data. So, same optimizer, same everything else. We can look at the network again. We can fit it again. So 20 epochs, same as before. Note that now it's taking like This was just on my laptop. It took about 30 seconds per epoch, as opposed to, what was it up here, 1 second. So it's a bigger model, multiple layers, takes longer, but still, totally doable on a laptop. And yeah, so overall still looks similar, but it is a little bit better, if I recall correctly, right? So this is like 88% accuracy and validation. Here we had something like 87. So maybe it's a little bit bigger, but it's still overfitting, right? How can we tell? Well, the curves are divergent. So let's add more dropout. So now I did the same thing, except I made dropout 50% instead of 20%. The other thing you could do is you could add more data if I had more data, but I don't. So more dropout is a good way to make up for more data. Now these curves making it look much happier. They're actually tracking each other much more closely, right? And so it's funny, right? Because your accuracy curve is actually way lower now. And it's taking longer to learn because, network is trying to learn stuff and say, great, I've set these weights to be just right. And then the next data point comes along and you're like, whack, half the weights go away. And this keeps happening. So it's harder to learn, but if you learn, it's actually learning something that generalizes, right? So you can actually see the validation numbers are in line. So I trained some more. The scale, basically it's flat after a while because the scale is different. So fine. You could go further if you were trying to do this for real. We'll see more examples where we do go further. This was just sort of an intro example for how this works, right? So now I say, okay, you know what? I'm not going to fiddle with it anymore. Let me look at my test accuracy. I get 93%. One quick note on this data set. You should be surprised that I got 93% on test accuracy because my validation was only like 89%. Like what's going on there? In this case, there's actually a good explanation, which is that the test set was manually curated, and so it doesn't have incorrect labels, whereas the training data is this giant set of things that were automatically put together and has about 3, 4, 5% mistakes. So that explains why that is. Okay. And then, a few other questions, right? I didn't answer, like, why did I start with 20% dropout? Why did I switch to 50? Why 2 hidden layers? Why not 3? Why 512, et cetera? The answer often is you got to try and see what works. And for the most part, you can cheat by trying to find other people who had success on a similar application and start with parameters kind of like those. But in general, this is where the art of fitting neural networks comes in. It's difficult. Okay, so I'm trying to remember if there was anything else I wanted to say before we move on to the next example. No, not really. Fine, so 3. So far, we've just been looking at these learning curves, right, where you can detect overfitting, underfitting. In general, it can be quite helpful to, understand what's happening in your network, right? And TensorFlow is cool, among other reasons, because it comes with this tool called TensorBoard, which can help you visualize stuff that's happening inside your network. So I'm just going to do a brief demo of what that looks like. And we'll see a little bit more again tomorrow as we go into sort of bigger, more complicated examples. So basically what you do is, everything is the same. You load your data, you get it in the right shape, you make your network. So then Keras has a way to sort of hook into the TensorBoard. You can say, periodically, call this function that I'm going to pass in, called TensorBoard. Where do I log information as I'm going? Do you want to actually visualize what the network looks like, et cetera? So you make this callback. You pass it into your fit function. And now what it's going to do is after every epoch, it's going to log a bunch of stuff to that directory. which TensorBoard can then read. And otherwise, it trains as usual, right? So we do the same training, so I can still look at this. But now you can actually run TensorBoard. Let me see if I can actually do this live. Set this up earlier, but we were at lunch. This. That's the right directory? Yes. So this is, some log files that I ran before. Wait, that's a weird URL. 6006 localhost 606. And you get this thing, which gives you, if you sort of hook it up correctly, a whole bunch of different visualizations, right? You can see the same curves I plotted before, accuracy, validation accuracy. Note there's multiple curves. That's because there were multiple runs that were logged to the same directory. So you can run things with different parameters and actually compare what was better. You can log particular images, either if you're doing a visual task and you want to, for example, log like, oh, here's the things you got mistakes on. That can show up here. If you're doing audio, you can log audio. You can see this is, I guess I'm zoomed in. You can see the computational graph. So zoom. Where you can actually see, okay, here's my hidden layers, here's my ReLU, here's kind of where everything is connected to. So for a big network, this is a useful tool for debugging. There are some best practices for how you structure your network and how you label the individual elements so that this looks like an organized network and not just a giant pile of edges. I didn't do here. You can look at distributions of various values. So here's, this sort of comes up to that important discussion we were having earlier, where you can see, okay, what are the values in hidden layer 1 of the biases, and sort of over as the epochs progress, what's going on with the range, etc. I'm not going to spend a ton of time on this in detail right now because it really depends on your network and what you're trying to optimize. But just want to point out this tool exists, and if you're going to actually build real systems, get it all hooked up right away at the beginning. And as you have questions of like, oh, I wonder why such and such is happening, this is a place you can go and look for how to do that. Yeah, so what else is there? I guess maybe I'll briefly show the histogram view if it works in this thing. You can actually look over time at a histogram of a particular, each particular sort of set of variables, so biases or weights. Yeah, so this is actually kind of interesting, right? So for hidden layer 1, it looks like the weight distribution doesn't really change over time, but the biases change, right? So somehow it's decided that, you know what, at least in distribution-wise, it's happy with whatever the initial weights were, and it's just shifting some of them, I guess, mostly down. So again, if you need a little bit more insight into the particular thing you're optimizing, but that can be a useful thing to notice. Like, oh, why isn't it learning, or why is it learning too slowly? You can kind of see what's happening here at the various levels. For example, your output, hopefully over time, starts to be this bimodal thing where it's predicting things that either is an A or isn't an A, and it's not somewhere in the middle. Questions, comments, concerns?
Yes, a question. So like on that so here, for example, you can kind of see like, okay, so it looks like I can just kind of make a line here or whatever, but it's
sorry for this one.
Linearly, yeah, with layers. Oh, look, the previous one.
Oh, this one here, yeah.
Yeah, so pretty linear, at the maximum. Can I just kind of? I guess I should be able to like pass to it, not just say, okay, so don't fit that weight, just fix it to linear.
Yeah, I mean, in general, right, you want to keep in mind that, I mean, even for this network, this is a distribution of, 512 numbers, right? If it's the, well, no, sorry, this is the output. So this is a distribution of 10 numbers across all my inputs. So it's a lot of data that's been summarized into the histogram. So it's not like each individual value is this. This is the distribution of outputs that you get as I run through my 50,000 training examples. And so if it's not changing, that tells you something. But it's still, even with all these tools, it's still hard to understand really what's going on. It's not like, oh, this particular weight should be set to 12. You're not going to be able to get to that level of detail except for really toy networks with just a couple of inputs. Like the playground we were looking at earlier, you can actually by hand look at it and say, oh, okay, I should make these weights such and such. But here you're still relying on gradient descent and getting some visibility into what it's doing. All right, so quickly, I'm trying to speed up a little bit just to give context so that we actually spend more time, hands-on playing with things. And also a lot of this stuff, I want to give you a first glance, and as we go through more examples over the next day and a half, I think it'll become more salient in some ways. Like, oh, okay, right, I've seen this before. Now I understand how it's being applied to convolutional networks or to, to a bigger example. So GPUs, maybe all I want to show here, well, two things I want to show here, right? I mentioned the GPUs make a big difference. So here I wanted to see, okay, does this actually bear out in real life, right? If I make a network, what happens? So I use AWS. I spun up an instance that has a GPU, and I said, great, do all the same stuff, set up, load my data, still the same data set, create a network. This one is a little bit more complicated. It's a convolutional network. So we'll talk about exactly how that works this afternoon. But yeah, multiple layers, same activations, dropout, etc. And you can tell it to use different devices when you run it. So this is all you have to do to tell it to use the CPU, right? So say with device CPU, make my model on the CPU, compile it, run it. And so I timed it. Takes 4 minutes or so per epoch for this particular model. And then I do exactly the same thing, except I say with device equals GPU. And I run it, and well, you can already tell it's much faster. They get the same performance, modulo some noise because they initialize at different values, etc. And so just plotting it, right, it's much, much, much faster in GPU. And this is still a small toy example where I didn't optimize the GPU behavior, right? Like the back size. If you make it as big as possible while still fitting in the GPU, it might be even bigger. So in some cases, people get speedups that are, 50 times more than CPU. So if you can, do your work on a machine with a GPU, right? Whether in the cloud or not in the cloud, unless you're really sort of playing around with really small models. Okay.
I mean, for real practical problems, if you don't have a GPU, you shouldn't even be looking at deep learning algorithms in the first place. Because, by the time you're going to be spending in terms of just using CPUs to get the convergence and the kind of accuracy you're looking for, you're probably using traditional algorithms and checking off.
It depends, right? I mean, there are something, I guess I would phrase it slightly differently in that it is so easy to get a GPU these days, on AWS or Google Cloud or wherever, or at some point, I guess, on IBM. I don't know when you guys will get to it. You might as well. Sometimes, there are certainly problems where people just don't have that much data, but neural networks are still maybe the best approach because you don't know what features to use. We'll actually see an example, I guess, tomorrow, where, I did it all on my laptop without a GPU, and I still got reasonable performance with just, a few thousand images.
So that's where I was going. In terms of, getting a system with 1050 or 1060, 1070, 1080 GPU cards, even without double precision, it's so affordable nowadays. And then you don't have to have a Tesla grade card to actually run these kinds of algorithms. And you get a significant speed up even with basic GPU cards now. So it is something you have to consider if you're writing deep learning algorithms.
Do you recommend, like for getting started with deep learning, do you recommend like building your own rig or your own machine? Is that kind of, or is that?
I don't think you need
kind of
to. No, even a gaming machine, like a simple Alienware or Asus or even Lenovo kinds of laptops with at least like a 1060 with 6 gigabytes of RAM or 4 gigabytes of RAM should be a good place to start with some simpler algorithms. Once you prototype stuff and you're comfortable that you're working on something interesting, then you can always scale it on the cloud.
Sure.
But even to like when I try it out, I have my own tricks and things. I try for 10 or 15 epochs. Then I see what kind of parameters I can change and then see whether it makes sense. Because in some cases I demonstrate to my students, if I run it without a GPU, even to run like a couple of epochs, I'm sitting there for like 8 to 10 minutes. And at that point, there's no point in trying to run significant experiments without a GPU.
I think it really depends how serious you are, right? If you're just trying to get a sense of how deep learning works, there are plenty of toy problems you can run on a modern laptop quickly enough. If you're like, I'm going to do this for real, I'm going to go, play with Kaggle competitions, bigger data sets, etc. Either get a machine with a GPU or just forget it, I'm using AWS. Honestly, I would recommend AWS at first, right? If you say, I'm doing this a lot, my AWS goes going to get pretty high pretty quickly, I want to run experiments kind of full time while I'm asleep, then yeah, building your own machine or buying something makes total sense because you can cover the cost with a month of cloud time if you're using it full time. But for this, when I was developing this stuff, even the bigger experiments, right? You spin up a machine, you run it for 2 hours, you turn it off. It costs you $1.50. Like it's going to take me a lot of time to use enough of that to buy a computer. Not to mention our conversation from lunch of, do I want to spend the time like building my own thing and debugging, IRQ conflicts or whatever?
Today's i7 comes GPU. I saw they have.
For what?
i7 Intel chip. That comes GPU already.
Well,
No,
most
so
of the libraries with respect to GPUs we are using are NVIDIA.
Oh, they have to use
libraries, so you have to
Yeah, so they'll use CUDA. There are some libraries that work with other cards,
most
but
popular
they're not as good.
libraries use CUDA and so.
Intel chips do have some parallelization instructions that help speed things up somewhat, but not as much, right? So they can do I don't know exactly how many instructions in parallel, but we're talking maybe 8 instead of 1,000
640.
or 600 or something.
Okay, so when you say GPU, you talk about, if you're not talking about Intel, you're talking
At least,
about,
well, for TensorFlow today, you need a CUDA compatible card, so that means NVIDIA. Some of the other libraries, I think, are actually optimized for other, OpenCL and for other cards. All right, so maybe another. I want to give people a very, very brief glance at what it looks like to code in TensorFlow directly. We're using Keras for a reason, but underneath the hood is still TensorFlow. And if you really start using, if you get serious about this, you decide to really build these systems, even if you use Keras, it's still a bit of a leaky abstraction in the sense that sometimes things break, or sometimes if you're debugging using TensorBoard, that's showing you the TensorFlow stuff. So it's helpful to understand what's happening under the hood. And I would definitely encourage looking through a TensorFlow tutorial, et cetera. In fact, this code is based on one of those, modified a bit. So yeah, this is more or less the same thing we just did. Same non-MNIST classification, but now in TensorFlow. So data stuff is all exactly the same. Yeah, so TensorFlow, you have to work at a lower level, right? So rather than just saying, give me a layer with 512 units in this activation function, you actually have to specify individual weights and biases and so on, right? So you say, look, I'm going to have these inputs that are constants that I'm going to feed in. and I'm going to have variable vector or matrix, I guess, for my weights. That's this size, right? 784 by 10. And I'm going to have 10 biases. And I'm going to compute my logits, right? To do the matrix multiplication, add the biases, compute the error or the loss with a cross entropy function, optimize using this particular optimizer with these parameters, do the softmax, etc. Then when you train it, you basically, you have to actually do the epoch stuff yourself, right? At least this is the base model where you say, okay, for each step, like go run this optimizer with this loss function every now and then, print out some stuff, right? What's the loss and the accuracy, etc. Yeah, so this over here was using sort of pure gradient descent. If you want to use stochastic gradient descent, you have to tell it to use a different optimizer. If you want, well,
Same data set or no?
yeah, same data set. It's comparable accuracy. Again, I wasn't trying to re-optimize for accuracy. I didn't train that long. If you have multiple layers, it helps to reorganize your code so you can, and this also adds the TensorBoard information so you can actually look at what's going on. But, this is, so starting from here, like, here's my inputs, here's the TensorBoard information to log, here's the actual network structure, because here's a way to make a hidden layer, and I call it twice, I think. I guess just once in this one. Oh, no, yeah, for multiple layers, I make the layers, give it the right name. Here's the loss function, here's the actual training function. Here's how I'm going to actually predict this thing, put it all together, doing the data batching, and then here's how you run the experiment, right? It's like, short version is you have a lot more control over exactly how everything works, but the trade-off is I can't fit the code on the slide anymore. It's a few pages. It's still it's still much more concise than if you started from scratch in a blank code window and had to go write your own neural network. But use Keras to start. Yeah, you can plot things, etc. So that's all I wanted to say on TensorFlow directly at least for today.
Keras is getting integrated in the TensorFlow distribution, so there's going to be a lot more integrated support with TensorFlow anyways. So the ecosystem is getting a lot more mature. So it may be a good idea if you're never used deep learning to get familiar with the TensorFlow structuring of the network. How do you set up a sequential network? How do you add the layers? How do you parameterize various things? You get a feel for the workflow, and then start exploring other architectures. And TensorFlow is probably the tool to go once you're kind of deep into the woods and you want to do very intricate configuration of this or work.
Even then, right? You can use both Keras and TensorFlow, and they interchange very well. So, if you're doing a mostly standard thing where you have some custom components, like, oh, I want to have a new type of, I don't know, of activation function I want to try. You can code that up in TensorFlow and just hook it up here, write everything else in Keras and just use that, etc. If you want to have some kind of funkily structured network, you can still specify that in Keras and drop down to TensorFlow only when necessary. So I guess, yeah, high-level suggestion is it's worth understanding how TensorFlow works, but it's not a good idea probably to spend most of your time actually working in it directly. And also, feel free to ignore that once you know enough to say, no, I know what I'm doing. I'm going to use whatever I want to use. Okay, so that was some demos just to get you a sense of what the code looks like. Now switching gears back to sort of more, I don't know, theory isn't really the right word, but to neural network organization, right? Different ways you can structure your network to get better behavior, get better performance. Specifically, we're going to talk about convolutional networks for vision. Someone mentioned I guess you mentioned, I think, in the morning, right, that you want to learn more about convolutional networks. So there we go. Right. So what are we talking about? You know, what are they? Why are they useful? Let's look at how they actually work in code. Again, for our favorite letter classification problem, and then let's look at it for more interesting vision problems that aren't just text, and also the fact that you can use them for things that aren't just classifying things and not just for vision. So here's our input, or our picture that we sort of saw before. Right, let's say we resize our images so they're not quite so big, but still we have 60,000 pixels in this image of a cat, 300 by 200, and we're going to have a bunch of layers, and we're going to try to classify, what kind of image this is. And our network is going to learn things like, learn useful features. And so these low-level layers are supposed to learn, for example, if there are corners or lines or edges, and then we're going to put those together into high-level things. So, this neuron that I've highlighted might learn at some point, I'm going to activate and have a high value when at this particular location in the image, there's a pointy corner facing up, right? That might be an ear or part of an ear, right? If later on we can combine that with other features around it to decide whether it's an ear. So why is this maybe not the way you'd want to do visual processing?
Too many variables.
Too many variables? What do you mean? Can you elaborate?
Just you have too much framework here. It's just all these connections, they're all independent for each other.
Right. You have lots of connections. Each of these weights, right? Everything connects to everything else, and for every set of layers, and you have to learn all of these weights separately, right? So here you might have a different feature that's learning, okay, still a pointy corner, but at a different location. And in order to learn the same thing at a different location, you have to set a whole new set of weights from all your 50,000 inputs to that unit that I've highlighted, and set them more or less the same way as the previous one, right? And the same thing for everywhere else. And so essentially, yeah, you have to learn independently at every pixel what's important at every location in the image. And that's silly because we know something about images, right? We sort of assume that, look, if I have this cat and I shift it one pixel to the right, still a cat. If I flip it around, still a cat. If I zoom in or zoom out, it's still a cat. If I put it in a slightly different orientation. And so that's one, right? Spatial invariance. There's other assumptions I can make that say, look, visually speaking, typically things that are close together are more important. And sort of once I understand the structure locally, I can understand the global picture at a higher level. Right? So just thinking about it intuitively, as I look at this room, I don't really care about the exact pattern of reflections on the top of that chair. I say, look, there's like chair there, person here, chair there, etc. And I don't need to understand the whole picture to sort of identify individual objects. So I should be able to do things locally and only then build things up, which I guess comes to the last point, right? That there's this natural spatial hierarchy. I can look at things locally, and then over time build up a bigger picture at a much higher level of abstraction, right? So like the representation point I made earlier this morning, it's much easier for me to understand this as a cat if the things I'm looking at are things like, tails and ears and eyes and whiskers, not 60,000 pixels. So what are we going to do to reduce the number of parameters and make our problem simpler, given those assumptions that we can make about visual data? Anyone? What are some things you might be able to do?
Is there a way we can do some kind of dimensionality reduction before going into the network? So rather than something that maybe capture some of those like some of the PCA or something like that, where you're getting most of the variance and then passing that along. Basically, like dimensionality.
Right. So one suggestion is we can do basic pre-processing and do dimensionality reduction. That is something people do sometimes do. I think well, yeah, it can actually be useful in practice. Part of the theory is, we want the network to learn what's important. So that is a good idea, but that's not what I'm suggesting here. So let's say locality, right? I'm going to assume that, I think that the top left corner and the bottom right corner of the image probably don't have that much to do with each other. How might I encode that into my network structure?
You want to using the locality, local information.
Right.
You want to somewhat create a filter by nearby information.
Right. So the idea is I'm only gonna look at local stuff, basically. Right. So use a filter of local information. One way you can think about translating that is to say, look, rather than connecting every single input to every single one of my hidden units, let me just take a local group of pixels and say, okay, learn some weights for these pixels and connect them to a node that's going to compute something about that area, but not connect all 60,000 of them. Right? Maybe say, let me look at groups of 10 pixels at a time, or 20 or 50. And then, further down the line, I can then connect those groups and still get back that ability to understand what's happening across the image, but not at the pixel level. Okay, what about for spatial invariance? Right? If I'm saying, look, a cat ear over here is the same thing as a cat ear somewhere else, how can I encode that in my network structure? What does it mean about our weights? Same weights, right? So if I'm using one set of weights to look at a region of an image in the top left of the image, I should use the same weights to look at a region at the bottom right of the image. And now, rather than having to run a separate set of weights for every single pixel, I just have to run one set of weights that I'm going to use throughout the whole image. So yeah, those are the basic ideas. So let's look at this in terms of pictures, right? So locality, rather than connecting all of my inputs to every single one of my hidden units, I'm going to say, what? This is a 1D example, but do the same thing, obviously, more dimensions. I'm going to look at just 3 pixels at a time, 3 inputs at a time, and say, look, each of these hidden units is only going to be a function of the 3 connections next to it. And then for invariance, I can say, what? For each of these hidden units, the 3 weights leading into it are going to be the same. Right? So now, even though I have a lot of edges here, I can still only run 3 weights, right? What do I do with the leftmost one, the middle one, and with the right one, feeding into each unit? So now I've gone from, however many, right? It would have been 8 times 7, 56 different weights to 3. And that means that, if I can set those weights efficiently, my network has, much less to learn, and so it's going to learn faster.
When you say the same weight, what does that mean? It means x0, x1, x2 using the same weight, and x1, x2, x3?
No. So yeah, that's a good question. This weight, the connection from x0 to this unit is going to be the same weight as the connection from x1 to this unit. Right? And same here, etc. So it's still 3 different weights. So for example, we'll hold that thought for a second. Yeah. One way to think about this is that I'm going to take a set of 3 weights and slide it across this vector, and sort of at each point, take the same 3 weights, do the multiplication, and get a value. Right? So for these 3, I get this value. For these 3, I get this value. For these 3, I get this value, etc.
And you get a bias.
Yeah, so there's still a bias, but there's also only one bias, right? So it's still, I'm doing the same, sum of weights times, wx plus bias, but there's the same w at each point. In general, it's 2-dimensional for image data. So I'm going to slide a 2-dimensional little square, typically. in convolutions is a thing that sort of exists in mathematics and image processing as well. Often they call this thing the kernel, right? So that's the set of weights I'm going to use, and I do a linear combination of that with a particular set of pixels somewhere in the image, and that gives me an output value. And then I slide the kernel over one, and I do the linear combination with the same weights, and it gives me the next output value, and so on. So this way you can kind of slide the filter across the image, at each point get a value, and what that's giving you is whatever you can think of this kernel as a detector for something. For example, it could be it can detect edges if you set up the values correctly. I think I have an example in the next slide. Yeah. So, well, I guess I just gave away the answer, but right, this set of values in this kernel is going to detect vertical edges. Essentially, if you have if you have a flat area with sort of constant color, then let's say all the values are 20, right? Then you have 1 times 20 on the left, sorry, on the right, and you have -1 times 20 on the left, and you add it all up and you get 0. Whereas if you have an edge going, I guess in this case it's going from light to dark, depending on how you structure things, right? If on the left you have a bunch of zeros, then you have an edge, and then you have a bunch of 20s, then you're going to get 20 times 1 plus 20 times 1 plus 20 times 1 minus 0, and you're going to get a large positive value. So if you slide this kind of filter across an image, you're going to get a high value only where there are edges from left to right, light to dark. And you can do the opposite and get edges the other way, etc. Now, of course, again, this is where in image processing, people spend a lot of time coming up with convolutions to detect various things, right? Detect textures, detect edges, vertical, sideways, etc. We're going to have the network figure that out. So we just say, the network, you get 9 weights, go crazy. Figure out what 9 weights you want to use to get you something useful. And yeah, so 2D looks kind of like this, right? You have, colors are very different. Angles different. Yeah, so you're going to have each layer in your hidden layer be, kind of have a view on some small part of the image. And if it fires, that means that whatever feature you're detecting is there. So sometimes people call this a feature map, right? That says, look, I'm telling you where features are or aren't present. And then you can do the same thing again, right? So now we have a feature map of those A's. You can think of it as just an image that has a bunch of pixel values, right? Things are high or low, etc. And now we can do it again. And do another convolution, say, okay, now I'm going to pick again one set of weights. I'm going to slide across this whole feature map and figure out what new values to have. So this way, if you notice, right, this x00 point only has an influence on that bottom corner at the A level, but then over time, you can actually sort of aggregate information if you have more and more of these layers. The further down in the network you are, the more of the image, it's called a receptive field of a particular unit. It gets bigger and bigger as you go. And so eventually you can actually have things that indirectly depend on a large part of the image. Other things people do is, this trick called pooling well, it does 2 things. It reduces the dimensionality, so it just makes less computation. And it also gives you a bit of a spatial invariance. So the idea is I can say, okay, you know what? I'm going to look at every 2x2 or 3x3 part of my image and just take the maximum value out of those 4 or 9 or however many you want pixels. And the benefit is basically that means is if, again, in the cartoon intuition is if I have an ear detector, I don't really care where the ear is, right? If it's off by a couple of pixels left or right, it probably doesn't matter for high-level image analysis. And so I can say, just give me the max, right? If this feature is present anywhere in this area, I'm just going to have a high value. And I don't really care which particular location it is. So this gives you some invariance to sort of wiggling things around, and reduces, by a factor of 4 or 9 or however big you want to do, the amount of data you have to then deal with further down the network. Finally, what really you would do is rather than doing one feature map at each level, right? So compute, have one set of weights and just compute that, kind of like we had multiple units before. Now you would have multiple layers of features, right? So in this example, it's from this paper, you have, say, 4 feature maps at the first level. So you say, I'm going to learn 4 different sets of weights. And again, this sort of intuitively means, look, one of them might learn to detect light areas, one might learn to detect dark areas, one might learn to detect, vertical edges, horizontal edges, etc. And yeah, so I'm going to learn a set of feature maps, and then the next layer can then actually look at still a small spatial area, but can look across all the feature maps. Well, I guess here they have a subsampling thing, right? So that's kind of like the max pooling, which they look, let's just reduce it by a factor of 4 to in each direction. But then when you're going from C1 to S2 there, I guess yeah, it has the picture, right? So you're doing 6 sets of weights. For each set of weights is taking a small patch at all feature maps. And so again, intuition is I want to find places that have a horizontal edge and are dark and do not have a vertical edge nearby. And I'm going to activate for that, right? So you're actually looking at a 3D volume at some small location across the feature map. I think I have some more pictures of this. Here's another example. Right, where you start with 256 by 256 by 3 for the red, green, blue colors of an image, and then you compute 16 different features. Let's say slide anything 2 pixels at a time, so you reduce the spatial dimension by a factor of 2 in each direction. But now you have 16 features instead of just 3 colors. And now, to go from that to the next level, I'm going to have 64 different filters, where each filter is looking at, each filter is looking at all 16 channels. Right, so it might be a 2 by 2 by 16 set of weights, and I have 64 of those filters, and so then now I have a representation that's, again, sort of more semantically deep. I have 64 different things I know about what's happening at each location. But each of them, I only have that once every 4 pixels in each direction, etc. Does that make sense?
When you do 256, when you do the first layer, you do 2 by 2. In the 256 by 256, you reduce to 128 by 128. You do 2 by 2 as your convolution.
So there's 2 ways you can do that. Well, at least 2 ways you can do that. The convolution size actually doesn't matter. You can take a convolution of whatever size you want and just jump it 2 pixels at a time.
Yeah.
Okay. Right. So then you reduce resolution.
So you can do not 3 by 3, but you jump.
But jump 2.
Okay. You can even do 5 by 5.
Right. You can jump 2. So let's go to stride. You can say, look, I'm going to go stride 1. That's sort of the default, but you can do stride 2, stride 3. You can also do what we just saw before with pooling, right? So do it at every point, and then do something like max or average pooling to say, look, give me the maximum value from these 4 pixels and these 4 pixels and these 4 pixels, which again reduces it by a factor of 2.
Yeah. So actually, when you reduce the first layer, you have to do pooling. You also need to do pooling.
So you can do either stride
slide and pooling, right?
or pooling.
Or you can do.
I mean, you can do both, but stride reduces dimensionality, right? So if I started with 256 by 256 and I jump every other pixel, I'm going to get 128 by 128. Or I could not do stride. I could do every point, and then as a second step, I can do pooling. You could do both if you want to, right? Pooling is a little bit different in that it gives you the spatial invariance. It's more computation, but it means that if the feature was sensitive to location, and sort of you skipped it when you jumped over it with stride 2, now you're going to detect it and then do a dimensionality reduction. The other thing that's important, right, is it's not actually 2 by 2 or 3 by 3 or whatever it is. It's 2 by 2 by 3 at the first level, right? Because I need one weight for each of red, green, and blue at each pixel position. And that's, once you understand that, that gives you the, okay, at the next level, it's whatever it is, 3 by 3 by 16. And so on. So each filter is looking across all the features, which is how you actually get power, right? You can actually say things that are interesting, in math, but intuitively it's saying things like, okay, I want places that have an ear, have a thing that looks like an ear, and nearby has a thing that looks like another ear, and nearby have a thing that looks like an eye. And if I see that, then maybe there's a face here. So because you can add up things across all the feature levels, you can learn these complicated things.
So the first layer, you do 16 filters, right? Because
Yep.
But you input your RGB 3 color, so you apply all 3 colors into this 16.
Each of the 16 filters is looking at some spatial range and all colors. So you're always looking at some, typically people will say just the spatial size. So they'll say, I'm using a 3 by 3 convolution. What they actually mean is 3 by 3 by however many features I have. And so the initial input is 6 by 2 to 6 by 3 features, where the feature is how much red, how much green, how much blue. The next level is 16 filters. And so at that point, for the next step, it's, okay, I'm going to look at, again, maybe say 3 by 3 by 16. So I have a weight that says, okay, in this location, if there's horizontal edge, a vertical edge, a dark area, a light area, texture transition, et cetera, I add all that up using this set of weights, and that gives me one of the feature maps in the third layer. And I do that 64 different times with 64 different sets of weights.
In terms of like the image itself contains, the whole information is really 56 by 56 times 3.
Yep.
Like that's the whole information about the image. Now, like at each layer, so I'm wondering, like, is there like some sort of like a rule that you can't like go too far like from that information, right? Is that such a thing?
I think so. I think what you're asking is, for example, here, right, the second layer, even though I've reduced the spatial dimensionality, actually has way more numbers, right? Because it's 128 by 28 by 16 instead of 3. So I actually increased the amount of data I have. And does that make sense? Like, if I keep doing that, am I just going to have very sparse or kind of random numbers? Is that a good?
Yeah, to me it sounds like I'm just like, once I read the paper, which had like 18 pages, and they had like 25 data points, and they put like all sorts of graphs and like,
sure, right,
sort of analysis on like 25 data points. I feel like that's a little bit too much,
right.
Analysis on like.
Right. So the question is, how much information can you actually get out? Well, I think that's a good question. In general, yeah, I mean, to some degree, you have to match the complexity of your network to the complexity of your inputs, right? So if you're doing, these character recognition networks, where you start with a small black and white image, you probably don't need like a 20-layer deep, super wide, many feature network. If you're trying to analyze, sort of typical visual data in color and just in the full complexity of the world, you're going to need a more capacity in your network to be able to represent, bigger filters typically for visual data and more of them, because it actually does matter, right? In the world, you need to recognize weird textures and shininess and lines and edges and curves and all that stuff matters. So you're going to need more features to represent that. Okay, what's going on at this particular point of this photo? There's a lot going on, so you need to be able to represent that. To some degree, again, the network will figure it out. You can try. Well, we'll see a little bit of this later. Actually, we'll see a little bit of this in like a minute. You can try to reduce the dimensionality and try to make the network say, you know what? Can you compress all that stuff in all of these numbers down to a smaller? smaller representation in a way that's still useful. And if the network can figure out how to do that, then you do better because you have fewer numbers to deal with. If your performance drops when you do that, then you go back and you take that out. Go ahead.
Yeah, so a question on the like 16 layer feature layers. So if you're doing that with the same input for each of them is the same sliding group of inputs.
Yep.
Then is the different thing that is detecting or different features detecting based on the initial weights that it's being set up? Okay, so you just have
initialize them all randomly.
And then it'll just learn different things.
Yeah. So the question is, how do you get, why do you get 16 different filters if they're all using the same inputs? And yeah, the answer is you initialize them randomly, and then as the network learns, as some of them start to specialize, right? So as one of those features is like detecting vertical edges, there's going to be less value in making another one do the same thing, and so the gradients will tend to push them into doing different. That's a very high-level canned-wavy explanation, but essentially that seems to be what happens, right? Well, I think I have some pictures in a second here, actually. But yeah, you have to absolutely initialize things differently. If you initialize them all to the same values, they're going to go in lockstep and keep being exactly the same. Right, I guess I already talked about that. So when you say 3 by 3, if you see any papers, they always have that. It's always by depth. In principle, you could actually do something more complicated, but that's pretty much never what people do. Right, so still, right, you still have bias. Sorry, go ahead.
One last question at the end, the classifier stuff.
Yep.
Could you, and I'm not sure if I missed that when you were explaining it, but what exactly, so I see that there, so it's 256 feature layers, or the depth is that? So is that where it's actually trying to classify every pixel in the?
So,
or
hold that thought.
Okay.
The question is, okay, so how do we actually get a classifier of this, right? So far,
22.
over here, right, we've gotten to the point where now we have, a 32 by 32 spatial by 256 features thing, but that's still not a classifier, right? In the end, I need one number per class. So there's roughly 2 ways of doing that, and I think I'm about to talk about that. Yeah, so we talked about, well, first, right, after each layer, we still have our nonlinearities, rows, etc. I didn't really talk about this, but at the edges, as you're moving your convolution along, you need to decide what to do. If you only slide your filter over like actual input data, then you're going to reduce the size of your image, right? In that first example with the 1D, there were 9 inputs, but only 7 outputs, because you had a 3 by 3 filter, so you couldn't put it on the edges. You can do that, or you can often just pretend that there are zeros all around your data, and then you get sort of weird. It doesn't really make sense mathematically, but it seems to work, and you preserve the size as you go. We talked about stride, and this is the classification thing. What people sometimes do, typically did at least, is just have fully connected layers after your convolution, right? So if you go back to here, you would then have a layer that takes all 32 by 32 by 256 of these things, pretends it's just one big long flat vector, and does a regular multi-layer perceptron or one layer perceptron. So look, I'm going to have a hidden layer that connects all of those things. So now this gives me a chance to do any kind of global analysis of the image, and then use that to classify. Feed that to my output, softmax, etc. The other thing people sometimes do is, if you have, for example, 256 classes you were trying to do, is to make your last convolution that depth, and then just average across the spatial dimension. Right? So basically do this, and then say, okay, what, for each feature, just average it across those 32 by 32 pixels, and that's going to give me a vector of size 56, and then I can just do softmax on that and get my classifier. The advantage of that is that can deal with images of different size. Because then, I just reduce my resolution until I get the right number of feature maps. Each of those feature maps at that point is supposed to be learning something like, somewhere in this image is the thing I'm interested in. There's a cat, is feature 7, and there's a dog, is feature 8, and there's a car, is feature 9. and then I just average that across, either average or max, across the spatial dimension, and get back a classifier. So those are the two ways people do that. Yeah, so this is an interesting question. If you can answer it and you really understood what we were talking about. When we say one by one, what do we mean?
To the scale.
So go back here. When I say I'm doing a one by one convolution, let's say after this last layer, I'm going to do a one by one convolution.
It's fully connected.
Yeah, right? Because it's not one by one. It's one by depth. And so I'm still actually doing something interesting. Right? I'm taking all of my inputs at a certain fixed location in the image spatially, but across all the features. And so, for example, I could say, okay, look, 256 is too many. I don't want that many features. So I could do a one by one convolution with, say, 16 filters. And that's going to say at each location, so I'm still going to have 32 by 32 output, but at each location, take those 256 things and try to figure out how to summarize them into 16 different features that you could then do going forward. So it's a way to, and essentially, if you think about it, it's actually just a fully connected neural network on its side, right? Because I'm taking all my 256 things and I'm connecting them to 16 features at the next level. And I just do that mini fully connected network at each of my 32 by 32 locations. Right, so that's, yeah, so you're computing a weighted sum of my features at some level, and so you can make it learn, for example, to reduce dimensionality. Yeah, this is kind of a cool connection to make. And so you see that sometimes in papers where, again, they compute a bunch of features and then say, okay, let me summarize that. Let's see.
Is that every feature they have a different weight, or you want to put a 0 and 1?
Every feature has different weights, and the particular network has to run the weights, right?
So you're doing a linear combination of different features.
Yeah, and again, I mean, it's really exactly the same thing that we were doing with our fully connected networks before, where somehow you say, look, take all this input and represent it using these linear combinations and these weights in this more concise, typically, or at least in this different way that we think is going to be useful to do the next step. Right? So you can think of the neural network as sort of giving you a different representation of your data at each level. That may be you losing some details and gaining other details, and combining things in certain ways. Hopefully, in the end, it learns a good representation, whatever that means, for the problem at hand. And so this is just a way to kind of do that in a convolutional network. For training, backpropagation really pretty much just works, right? You compute your derivatives. Now you have, for each weight, it's used in a lot of different places. So you have to add up the contributions for each of those places it was used. But you just add them up, and you get your gradient updates the same way as before. Yeah. So here's an example from a paper that was doing, classification for images. It's a little hard to see, perhaps, but you take your image, you run a bunch of convolutions on it. So these are different filters, and you can kind of see vaguely. Where's my mouse? Here's my mouse. Right? That they're detecting different kinds of things, right? One of them over here is detecting like the reflection or the really bright white part over here. Some of them are detecting the shadow under the car. Some detect the sky, looks like. When you apply the ReLU, that's the activation function, right? You can actually see what fires. Right? So here you can actually see what's shown, right? This is the shadow under the car. So presumably it's looking for dark regions, right? It also fires over here where there's dark trees. Etc. So then you take a convolution on top of these features, and you're detecting other things. The early layers, especially if you look at them, more blown up, are typically fairly easy to understand what they're doing. As you get further down in the network, in some ways it's easier because you're like, oh, interesting, this thing fires, for a back window, but other things can be really hard to interpret. This is where, neural networks in particular have this reputation for being hard to understand because you have this giant pile of numbers at the end of your network, and even for visual data, it can be hard to understand. For non-visual data, it can be really hard to understand. But in the end, the point is, if things go well, it figures it out, right? Gradient descent just gives you good weights, and it says, hey, it's a car, not a horse. Here's another example of sort of what this kind of thing looks like in papers, or blog posts, if you're looking about convolutions. Now we can have all the tools to understand what's happening, right? So here it's saying, look, we start with images that are either 54 by 54 or 36 by 36. We do, depending on which it is, we do the 5 by 5 or 7 by 7 convolutions. So normalization, I guess we'll talk about a little bit later. Basically, you can renormalize the weights. That helps make training work better. We do pooling, right? So here there were 32 filters. Then we do it again with 3 by 3, 128 filters, etc. Do a bunch of times. Then we have 2 dense layers, and then we classify.
So how does this OR work? I'm not quite.
Sorry, how does it work?
I don't understand how, like you said, we can start with 2 different images. So how do you combine?
So I think the idea is I want to end up with 18 by 18 by 32, and then I'm going to do fixed stuff from there. So what they're saying is if you start with 36 by 36, then I'm going to use a 5 by 5 convolution with stride 2, presumably, or with pooling by 2. Right, so if I do 5 by 5, it's going to reduce my size down to 32. So yeah, no pooling then. If I start with 54 by 54, I do 7 by 7. I mean, so there are probably more details in the paper exactly what they did, but basically you can adjust the stride or the pooling to reduce by a factor of. That's weird, actually. A factor of what? A factor of
But even then, it's kind of hard. I don't see how this model actually because of from which side it goes.
Well, it's just code, right? So somewhere in the code it says if the input is this size, then the first step is this. Get me to something that's 18 by 18 by 32.
Yeah,
And if the first step, let's run it. I want 18 by 18. So here it's going to be right. The 5 by 5 cuts off 4 pixels around the edge, so I get 32 by 32, and then I can subsample that to 18. Here 7 by 7 cuts off 6 pixels around the edge. I get 48, and I can subsample by 3 to get 18 by 18.
I mean, it's 54 by 54, you just skip 3. Every time you skip 3, strike for 3, and 32 by 32 is strike for 2.
Strike 2, yeah.
So you get 18 by 18. So the key is you want to know if you have 2 different sizes of images. In the end, in the first iteration, you want to drop down the feature into 18 by 18.
Yeah. So it would be interesting because I don't know, if you could program something like this, in Keras or TensorFlow. There's no
No, you
I lost the mic. That's bad.
So you say your input layer, how many things you want, and what's the
You can program it, but it's not going to be sort of a straightforward sequential model that we've seen before. I think there's a way to say, basically have an if statement. All right, I need to go to the bathroom, so let's take a break, and then we'll continue. I will be back in a minute. Also, can I get my water?
So great. So for plan, try to do the DXX.
Yep.
When I create a new IBM, I use my Yahoo.
Okay.
So, and every time I try to initialize the account, it fail. Don't know why. So I just log into my IBM ID. So and then you start to initialize the environment and it just fail.
Okay.
So I don't know.
And this is when you're logging in with your Yahoo?
Yeah, this is my I think it's my Yahoo.
Okay.
So
I think I saw something about this, that there was more issues with object storage, where it's like when it's trying to set up the object storage, it's like timing out, and so then it just comes there as it fails.
Okay.
So let's see if it goes through this time.
so I create ID only. It didn't. I mean, so you still cannot have my name to a project. I need to have
An
the
account set up.
DXS account set up. I think that's fine. Yeah, I want to see the simple code. Because look at the screen, it's very difficult to see the simple code. If I can see a simple code, it's easier to follow. But I don't know why.
Okay.
I expect the error will occur. So, do you want me to try again? I think I tried multiple times.
And you get to do this stuff.
Oh, no, this is the first time I see.
Let's try you selection one.
So which organization I need to do? My own?
Yeah, whatever, yeah, that's the only option, unless you want to create a new one, but it's probably easy just to do.
And I using the select DXS. So this is the one.
Yeah.
Space.
So if you, yeah, let's see, you put dragging. Yeah, let's just, maybe, are you on Slack?
Yeah, I can be on Slack.
Are you in
Which Slack you want me to
are you in the Watson data platform? Or where, I mean, or I guess same time might be easier, are you on the same time?
Yeah, I can.
Can you send me your, like, both accounts that you've tried to use?
Sure.
Or your email address?
Yeah. This is the first one.
Was that the one that we were just trying?
Yeah.
Okay.
And the second one, I think I created, but so it doesn't see it. So
Okay.
I didn't.
Can you try logging in with your IBM one?
Sure.
Make sure to share it on the
Okay, we're starting again. So let's go back to our pretty pictures. And hit the button. A couple more examples that I think hopefully give some sense of how this works. I guess, well, one thing to note here again, right? Here we have those dense layers at the end to take our, output of the convolutions and put it all together into a classification. This is a pose estimation paper, so kind of what position someone's in. Here's an example of the features or some visualization of the features that are actually learned by these networks. So this is from think from ImageNet. So from like photos of the world, right? So this is general visual data, and it's a 5-level network, 5-layer convolution. And what you do is you can actually you can basically figure out using gradient ascent, like what input will make a particular unit really happy, right? So how do I maximize the activation of this unit? You can randomly initialize an image and adjust the pixel values of the image to maximize the value of that unit, right? So of this filter. So that's how this was generated. And so in the first layer, you can see, right, it's learning very local things. So I think I forget exactly how big the filters are here, but they must be more than 3 by 3, right? There looks like there are things like maybe 7 by 7 or 11 by 11, like fairly large, enough to capture some of these wavy, textury things. And so it's detecting different colors, it's detecting different types of textures, and detecting different types of, I don't know what to call it, right? There's sort of color texture and there's like shape texture. These funny wavy lines. Yes. So that's what I was trying to explain. Here, what actually this is the author of Keras, has done is try to figure out what image as input makes the output, the activation of a particular filter as high as possible. And so you can basically use gradient ascent to say, how do I change my input image, to increase the values, the activation values for filter 1, filter 2, filter 3, etc. And you can just do that again. You do gradient ascent, and you get something that gives you some sense of what kind of patterns make that filter activate. So that's what these are. Yeah. So these are not the individual filter, like it's not an 11 by 11 kind of thing. Right. These are, so for each filter, you can separately run this gradient ascent problem. You start with a random image and you adjust the pixels until it makes the activations as high as possible. And that gives you a picture. So for example, this top left image says one of the filters in the first layer of the network seems to really like kind of beige with some spots in it. And so if your image somewhere, not in the whole image, but if there's some part of the image that's beige with some spots in it, that filter is going to activate. And if in some other part of the image there's horizontal wavy lines, then the one right below it's going to activate. And probably if you have wavy lines that are beige, they'll both activate. Right. So then the second layer, sorry, getting stuck on the microphone cord here, is detecting things that are a little bit more visually complicated, right? It's sort of still similar wavy patterns at different orientations, but now it's sort of saying, look, if there's an area that's sort of spotted or has these weird green and purple lines in it, etc., these various filters will activate. And again, at a particular location on the image, if you see something like this, it's gonna that filter will be on in that location. As you go down, you get sort of more and more complicated things, right? So the next level is really starting to sort of see like dots and I don't know how to pronounce this word, moire. Stripes with sort of dark to light patterns, crisscrossy things. At the fourth layer, you really start to get things that seem significantly more complicated, right? Sort of much less local features, right? So now you're getting, I don't know, things that look like pheasant tails to me, and amoeba things, and so on. And then if you look at the fifth layer, it's even more non-local features, activate those. And so at this point, you can start to see how, if I look at, there's 512, of which only 10 are shown here, features like this. And if I tell you, okay, at each one of these, at some location in the image, for each of these 512 filters, how much of that kind of pattern is present, you can start to see how you could use that to pretty easily classify, pheasants from dogs, from cats, from cars, et cetera. You're like, oh, look, if all these organic-looking sort of curvy, bumpy things are happening, it's probably not a car. There's going to be other features that are more about straight lines and really dark areas, really light areas. Maybe that's a car, et cetera. You can actually, of course, look for a particular image which things activate. Though again, at scale, it's just it's hard to make sense of it in our heads. But this hopefully gives some intuition for the kind of things that these things learn. And also, I think, gives us this idea of gradient descent, right? Of how do I take an image and fiddle with it to increase something? So that style transfer thing that you showed earlier probably has some element of that, right? It says, well, take this image and try to change it so as to maximize maximize how much it looks like some other image in terms of style, right? That's how you would do style transfer, I think. So let's look at what this looks like in code. And this is also a good time to ask questions, if you have them, on how this works. So let me stop this again.
So some of those images look like what you see coming out of the deep.
Yeah.
Is that essentially, so like you're saying, to maximize, is that kind of what it is, where it's doing the reverse, where it has an image and it tries to maximize one of those filters or something like that?
Right. It's trying to say, here, it's trying to maximize the activation of one particular filter. There's doing basically the same thing, except it's saying maximize the final output, right? So maximize the probability that this is a giraffe. And so how do I modify the image to make the probability of giraffe higher? And so then it's going to, back propagate, well, I guess forward propagate, whatever, the derivatives through all of these different filters at the same time and figure out, okay, so which of these filters do I need to activate to eventually make probability of giraffe be as high as possible? And so it's going to end up adding things that look like this into the image. Right, too many things all open. I guess I should log you out of data science experience. Do that. Boom. Not AI things here. So back to not MNIST. Now with more convolutions. Really looks pretty similar, right? So all the header stuff is exactly the same. Now we're going to have these convolution and max pooling layers. And we also have this new flatten layer, which just, takes an arbitrarily shaped tensor, pile of numbers, and pretends it's a vector, which is useful for then feeding into dense layers. So load the data, tell it, I just set some constants for how we're going to do our, how many filters to use and what kind of pooling to do and how big the convolution should be. Reshape things should be one hot. Here's our first model, right? So we start with a convolutional layer. Number of filters was, I think, 32. The kernel was 3 by 3. What do we do around the borders? So this is saying only keep areas where I have sort of all the pixels. So we're going to basically get rid of the edges. And what the input shape is, activation, that looks familiar. Do the same thing again, and then do max pooling, and then do dropout. and then flatten this into a vector, and then have a dense layer, and then do dropout, and then build our classifier, right? So actually go to the right number of classes, and then do the softmax. Hopefully, at this point, all of those things are familiar. We can look at, well, actually, here's an interesting exercise, right? So like, model the summary tells us how many parameters each layer has. So a good check, for this example and in general, as you're going through these things, to make sure you understand your network structure, is to be able to predict what those numbers are going to be. So let's actually quickly do that, right? So we start with our input, right? It's 784 pixels. And we're going to do a 3x3 convolution with 10 filters. So how many parameters is that? Right. So for each of these filters, we're going to have 3x3, 9 weights plus a bias. So we're going to have 10 parameters for each filter and 10 filters. So hopefully, is that right? Yeah. Oh, okay. I guess that's right, except that I lied. I actually have 32 filters. So for each of the 32 filters, I have 10 parameters, right? 9 weights, 1 bias. So let's go check that. 320, huzzah. What about the next level? Right, so now I'm going to take that 32 by, sorry. Well, yeah, I'm going to do 32 more filters, again, 3x3. It's still 32 depth. And
3 times 3 times 32 times 32.
Right. So again, here I'm thinking for each of my, right, for each of my filters, I have a 3x3 by 32 now set of weights. So whatever that is, plus a bias. And I have 32 of those.
I have a 3x3 filter, but I have 32 filters.
Well, no. I have 32 filters, and each filter is 3x3 by 32. Right, this is what we were talking about before. Each filter is looking at the whole depth, right? So I can actually add up what's going on at this location across all my different features. So, I mean, the basic value is, there's a lot more, right? Because now I'm looking at 32 feature maps at the same time, so there's more parameters. But still, if you remember, our non-convolutional networks had like 100,000 parameters for a relatively small layer. So it's still way, way, way smaller. And in fact, right here's our dense layer, going from 12 by 12 by 32, which is 4,600, to 128 hidden nodes. That's a lot of parameters that it's running. So most of the parameters in the convolutional network tend to still be in that dense layer at the end, if you have one. But a lot of the computation is still in the convolutional layers, because you're doing this convolutional operation, at every single pixel, or maybe you skip some. But yeah, so here's our model: convolution, activation, max pooling, dropout, etc. Looks very much like the code above. We can fit it. I was lazy. Sort of lazy, and didn't use a GPU, right? So I just ran it on my laptop. I took, a few minutes per epoch, but I went off and did something else. And we can look at how it's doing. One thing we notice is it actually generalizes pretty well, which is going to be a function of two things, right? One is the fact that I'm using convolutions. And so I'm giving the network much less freedom to sort of make up random crap at various points of the image. It has to use the same filters throughout. The others I'm using dropout. And the other thing we notice is that the test accuracy is 95%, whereas before it was like 93. So we actually got a big of a boost. But it's longer to train. Though GPUs really, really, really help a lot for convolutional networks because you're doing the same operation in a gazillion places, which is exactly what GPUs were built for. So if you use a GPU, it would actually be much faster. Yeah, so actually, if you remember the GPU example, it actually used the model was, in fact, a convolutional model. And so, again, without really any tuning for performance, you got a factor of about 10. Right? Well, here it was like a factor of 7. With tuning, it can be more. Right, so then I just ran it some more to see, okay, this looks like it's still going up. So let's see if it keeps going up. It didn't much. If you notice the scale, it's almost flat. And it's starting to overfit. Right, so training loss is dropping, still dropping, but the generalization loss is not really dropping much. So got about 2% better, still without really any optimization. I didn't explore a lot of parameters. I picked something that seemed plausible based on what I'd read before. So I don't know if I want to go through this. Maybe I'll briefly go through this. So what looking at the network summary above, I was like, look, all of the parameters you have to learn are in those dense layers. So maybe if I make that dense layer smaller and make it have to learn fewer parameters, it'll learn faster. So I kept the convolution layers the same, but instead of 128 hidden units, I put 48 in the dense layer. And ran the network, so it looks the same. Now it has only 200,000 instead of 600,000 parameters. Makes sense. But it doesn't actually help. It takes almost the same amount of time to train. This is what I was alluding to earlier. Most of the time actually goes into convolutions, right? Because I'm using those same weights, but I'm using them, at every single location. And in fact, if I'm doing a 3x3 convolution, at every location, I'm doing 9 different convolutions, right? As I sort of slide by the pixels. So it doesn't speed things up. It does, however, of course, hurt performance a bit because now I'm giving it less capacity. Well, it doesn't necessarily have to do that, but in this case, I gave it enough less capacity to actually hurt the performance, right? At some point, if I increase the network capacity by a factor of 10, it probably won't help that much. Because at some point, if I only have so much data, this was your point from earlier, if I only have so much data, you can only train so big of a network in a useful way. And so then if you reduce the capacity to a certain point, it won't really matter. It just makes your network be faster. And at a certain point, it starts to hurt. So then I said, OK, I want to make this faster, darn it. Let me try to use smaller convolutions. So I did 2x2 convolutions and did 10 filters instead of 32. So now it was much faster, right? So 40, 50 seconds per epoch instead of 230. But now the performance really went significantly worse because now I really didn't give it enough capacity to figure out all the important stuff. So general takeaways, tuning matters, both for performance and for computational performance and for accuracy. And you have options for trading those things off against each other, right? In particular, if you're building a model that you need to try lots of different variants, you might actually decide, you know what, I'm going to give up a % or 2 on accuracy in exchange for a 5x speed up, because then I can try way more things and get my work done sooner. Or maybe you'll say, you know what, that's not acceptable in my domain. So you have to decide in particular application. So that's the basic idea for convolutional networks. So let's talk a little bit about where they're being used in vision, and then we'll talk about where they're used not in vision. This was just a funny blog post from last year on Google's blog about cucumber sorting, right? So, the infrastructure is at the point where people can actually use this for relatively small scale problems, right? There's some Japanese farmer who was like, you know what, we spend way too many hours sorting cucumbers by size and shape into different buckets to sell them from our farm. So how about I build a little thing with TensorFlow and some cheap Arduino servo things to build a cucumber sorter. As of last August, they weren't doing very well in terms of accuracy because he was trying to train from scratch. But as you get more training data, it actually gets better. So yeah, you can do things that are sort of relatively simple. Here is this is Google's, right? So obviously, people are using this behind the scenes and lots of APIs that you can go out and get. So I went to Yosemite a couple months ago, and took this photo and just threw it in there and said, "Look, tell me what's in this photo." And it actually does a pretty good job, right? It says there's a forest, there's a vehicle, there's weather. Okay, I guess that's useful. It's winter, there's trees, etc. I threw it into Watson, which also did a reasonable job. It says it's a camping bus, which isn't quite right, but it's maybe not too far off. Vehicle, azure color, right? It noticed the sky, etc. So for vision, at least for general purpose vision of getting these kind of things, you don't even have to build anything these days. You can just go use an API, and I think people are doing lots of interesting things with with apps and visual stuff just by leveraging these tools that are out there. Of course, you could build it yourself if you want a particularly tuned set of labels.
A question for those two examples. As far as is there a trained model out there that's available? So you don't have to train the whole thing from scratch. You have you'd rather make an API calls for a bunch of photos and you just run it.
Yeah. So question is about whether there are trained models out there. There are trained models out there. ImageNet is sort of the standard, general purpose vision benchmark out there. So it has about 1,000 classes of different kinds of images, right? Lots of different species of dogs and cats and cars and ships and so on. So there are pre-trained models that get pretty good performance on that. And we'll talk a little bit later about how you can actually take that same model and use it for other purposes as well, where basically you rip off the classifier at the end, you put your own classifier, but on top of the features that we know are useful for doing visual tasks. So you can get pretty good results with limited data using those things. And in fact, I think I have it. Well, yeah, you're ahead of me by 2 slides. Use ImageNet models. Don't be a hero. Right, so this is still kind of vision, but now not 2D, but 3D, right? Same thing, really, math is all exactly the same. People are doing MRI analysis where you have a 3D image. You can still do convolutions. You say, look, I'm going to look at a small volume at a time, and I'm going to slide this cube throughout, my space, compute values, et cetera, et cetera. There's, by the way, 1 by 3. So 1 by 1 by 1 by however many features. Kernels again for dimensionality reduction looks like at the end. And then you get Yep.
I just wonder
how did they decide to do 25? So I think, again, there's there's 3 answers. One answer is you can just try different things and see what gives you good performance. And in the end, that's if you're really trying to optimize, you end up doing that in some range. 2 is you can see what other people have done, right? If you're doing fMRI analysis, you should go Google fMRI deep learning convolution, and people, probably using things from 15 to 40 or whatever. And 3, which maybe should have been 1, is to use some intuition you have for the task, right? So if you're a doctor and you're used to reading fMRI things, you kind of have a sense of, look, what size are the kinds of features that I'm likely to want to look at early on, right? I want to look at, looking at the image over here on the left, right? There's sort of shapes and curvatures and contrast changes. And so given the resolution of my fMRI, maybe those things tend to be 10, 15 pixels wide. And so I should be able to look at sort of a big enough area to detect them. You could almost certainly start with something smaller and just add a few more layers, right? So that's sort of a trade-off. You have, I mean, all the way from like fully connected on one end to like a whole pile of 3 by 3 layers in the other end, where you then sort of have to wait a long time before you can get to looking at kind of 25 by 25 by 25 at a time. So you're optimizing computational performance and yeah, sort of capacity. Yeah, and they decided that this was reasonable. You know, and so over time, it looks like for them at least, right? They're reducing 25, 21, 17, 13, 9 as they go, as they reduce the spatial complexity of the space. Right, vision. Andrej Karpathy, who you may have noticed in a lot of the little what's the word, references at the bottom right there, has done a bunch of work on neural networks and also published some great blog posts explaining how various things work. Right, if you're doing vision, even if you're not doing like real world vision, if you're doing medical stuff, still most likely you'll do better by taking a pre-trained ImageNet model and then adjusting it rather than doing your own thing from scratch. Exception being really, you know, if you're Google, or if you know, if you're IBM, right? If you have a huge amount of training data and a huge amount of computation, and you're trying to really fine-tune something, maybe you can start from scratch and just do that. Or if you're trying to win the next year's ImageNet. But for most of us, this is a great place to start, and then only go to not doing that if you really need to do something special. Right, so pre-trained networks, right? How do we do that? So I have another demo that says, look, it's great to build stuff from scratch, but why don't we take an ImageNet model and use it to classify cats and dogs? So VGG16 you mentioned earlier, I think you used for your Hulk mosaic. We use the same thing here to do, again, puppies and kittens because they're cute. Turn this off again, if I can find my mouse. So one thing to note, right, is ImageNet, as I mentioned, has a bunch of cat and dog classes in it already. So you would expect this to work well. But it turns out it actually works pretty well even for things that aren't already in ImageNet. So Kaggle had a dogs and cats competition a few years ago. And so I grabbed some data from there. They had a lot of images. We actually take a subset that's pretty small. So let's see, right? So I load the data. This is all the same. Just double check. So we have 1,000 training examples and 400 validation examples for each class. 2 classes. As always, it's a good idea to at least get a brief sense of what you're trying to classify. Right, so here's our cats, here's our dogs. You know, and we can see that there's like different positions, different backgrounds, different lighting, different whatever. So when this challenge was started 5 years ago or something, really state of the art was like, yeah, you could probably get 60% of this, but maybe 70. But you're not going to do very well because you know it's hard to describe what a dog looks like if you're trying to hard code it yourself. But neural networks have evolved. So we have 150 by 150 images. There's some magic you have to do to deal with the fact that TensorFlow and Theano store the multi-color images in a different order, whatever. Here's our network. First, I'm going to build my own network. Right, so convolution, max pooling, convolution, max pooling, convolution, max pooling, dense layer, classifier. Right, so now my classifier is just, you know, I only have one output because it's either a dog or if not a dog, then cat. What else am I doing? Oh yeah, so one trick that you can do, I was going to have a slide on that, maybe I haven't gotten to it yet. It's called data augmentation. So if you have a small amount of data, one thing you can do to pretend that you have more data is to take your existing data and massage it a little bit. So for images, You can zoom in and out a little bit. You can shear them left to right. You can flip them horizontally or vertically or whatever. The trick is to do that in a way that doesn't change the class label. Right? So for example, if you have letters, if you flip them around from left to right, then a B would become a D. And so if your labels would be wrong. But if you're just kind of tilting things left and right, if you're zooming in a little bit, that still preserves the class labels. And it gives your network more variety to train on. It's hard to analyze that theoretically because they're correlated images, but it still seems to work. So here, Keras has a thing that's built in for doing that for images. Say, look, I'm going to rescale. That just sort of normalizes the values to be smaller, which we like for performance reasons, but also shear by up to 20%, zoom by up to 20%, and randomly flip horizontally, but not vertically. Upside down cats are not very common. They're not that happens, but not that common. So we're not going to do that. At testing time, only do the rescaling, but not the other meshing stuff. So this is a way to say, look, generate data from this directory and do these modifications using this generator for training and for test. So find it, validate, so it still finds all the images. And then we say fit. This is a different version of the fit call where it takes this generator that keeps generating new things until we tell it to stop. And after we do that, we can actually save the weights so we can load them later. So this, again, not transfer learning from scratch. I'm getting validation accuracy of about 75%, which is already state of the art as of 5 or 6 years ago. But not as high as we like. So let's cheat, right? So what we're going to do is we're going to take this VGG16 model, which is sort of a real model that's a little bit out of date now, but it's pretty simple. Has a whole bunch of layers and one ImageNet, I forget, 4 years ago or something. We're going to rip off the top layer, which is their classifier, into 1,000 ImageNet classes, and we're going to replace it with our little mini classifier into our 2 classes. And so what that's going to do is it's going to give us a whole bunch of weights that are already there to compute the last level of sort of these bottleneck features that we know are useful for classifying visual data. And then we're going to have just a few weights to train in that final layer from those bottleneck features to our classifier. So you can do that in code. Keras conveniently has VGG16 built in. So you say, okay, I want that model. I don't want the top layer. I want to use the ImageNet weights that were published. And then say, okay, just take all my images and compute the values of those bottleneck, the last layer activations. You guys are all looking confused. I think there's a picture here somewhere that might help. Do I have a picture here? Sorry. No, I don't. I should have made a picture. Sorry, I'm lost in my file now. Here. So ask a question. Anyone?
For me, I'm not sure. So I get kind of the concept of what you're saying. I'm a little bit just like the details of. So you have the VGG16, which is the training class for 1,000 classes.
Yep.
Like for me, that's where the strip is. I'm not really understanding how we connect that with the one.
Sure. I thought I had. Oh yeah, here we go. Okay, so here's. Right. So here's the VGG16 model. Right. It has input. You feed it your 150 by 150, I think, or whatever the size was, images, and it has a whole giant pile of convolutions and max pooling and so on. Right. So there's like convolution, max pooling, max pooling, right? It keeps going for like 16 layers. It's been pre-trained, right? So we have a whole bunch of weights for all of those layers. And in the end, there's some layer that's, there's the final layer, which is 1,000 numbers, right? Probability for 1,000 classes. But before that is the last kind of hidden layer that has features that are useful to then generate those 1,000 probabilities. And so what we're going to do is we're going to just take away the connections from that last layer, last hidden layer, to the 1,000 output classes. And we're going to replace it with connections to a single output, is this a dog thing. And so now we're going to have however many activations there were, units there were in that last hidden layer. We're just going to have one weight, for each of those. We're going to take a weighted sum and, apply softmax, and that's going to give us a probability of dog. And the trick is, I can keep all the weights I had before, and so if I feed a new image, I can still compute all the same weights, compute activations at that last hidden layer, and now all I have to do is learn good weights for how do I combine those activations into is this a dog or a cat classifier? Does that make sense? I thought I had a picture in here somewhere, but maybe I didn't. I think I might have drawn one on the whiteboard last time. So I guess I could do it again. Well, let's just look at the code quickly, and then maybe that'll also help, right? So I take my model, and I say, look, load it with existing weights, and just get rid of the top layer. And then I'm going to say, just feed it all of my training images.
The top layer is the last one? Or the first
Sorry, yes, the last one. The classification, the 1,000
okay, the
output
last one.
classification. So I guess if you can just look at this model, right? Imagine if you had a toy model. I would say,
Oh, the top
get rid of this layer and give me just these 64. Right, so then I feed in an image and I get out 64 numbers, right? And then the network has been trained so that those 64 numbers encode the information I need to then do a good job classifying. So the original ImageNet thing, looks like this. It has 1,000 outputs. So I say, I don't want those 1,000. I'm gonna keep everything up here the same, and then I'm just gonna put in my own. Basically add this at the end, right? With or without dropout, but add just a single output. Or it could be more than one. In this case, it's just one. And you can also tell it, don't touch those weights that are there. Leave them alone. Just learn, the last set of weights. So that's what this does, right? Basically, it says, look, learn these activations. Not learn, just compute them. Right, I have a model, just run it and just figure out that last vector of the last hidden layer and just save those numbers. Right, so for each image, I now have a representation in terms of these bottleneck features. And now I can just make another model that takes, what is it? Yeah, I guess it was 4 by 4 by 512 was the shape of that last layer. And so I say, okay, take the 2,000 numbers I have, one for each of my training examples. For each of them, I have this vector, 4 by 4 by 512, of what the VGG16 model says are useful numbers to classify this thing. And then I'm going to I still add one more hidden layer. Which I didn't have to do. I could go straight from that to the classification, but I decided to add one more hidden layer, and then drop out, and then my classify, the output. And then say, okay, just given those feature vectors as input, figure out good weights so that I get good classification. And so I do that, and I save the weights for that top model. And yeah, so I train it. It trains really fast, right? Because I'm only doing like a small 2-layer network. And I only have 2,000 examples, so I don't have that much data to train it on. But I get pretty good accuracy, 90% or so on validation. Note that it's overfitting like crazy because I only have 2,000 examples. And I still have, I forget if I printed the summary, right? But I have 8,000 times 256, so a whole lot of parameters to play with. So it's overfitting, but still 90% is pretty good, better than 70 that we got before. And also you can notice, right, clearly I could have just stopped this after like 3 epochs. because it's actually getting worse over time here. So then, if you want to, you can actually, what's called fine tune. So basically, you can let it adjust the weights in the pre-trained model as well. Typically in just the last few layers. Right? So you say, look, the initial couple layers are probably quite good, right? There are general things like edge detection and textures and those things that we saw before. Those are really general, but maybe the last few layers, I can actually adjust the weights a little bit to be better for my data set and not for ships and planes and whatever else they were doing. So what you can do is do the same thing. Here's my top model that we had before. You can actually, and again, I'm not getting into the exact details of the Keras API, but you can tell it, oops, to make a model that sort of stacks these two together. It says, look, take as input the inputs of my base model, so these are the images, and take as output my top model, which I feed the output of my base model. So this basically just puts the whole thing together, including the VGG16 model and the our new sort of mini top for it into one single model. So you can look at it. Again, this is all the parts that are VGG16 with the 5 different blocks of convolutions and pooling. And then I have my sequential model here. Doesn't do a very good job visualizing, because really this internally just has a dense layer and the final output and a dropout. Yeah, so you can just look at the layers this way, and I say, look, I'm gonna tell it not to mess with the layers up through here, I think. I forget exactly how many I did. And then say, just adjust the weights in these last few layers, plus an RMOD. So you can just say, okay, layer that training equals false for the first 15 layers. Don't mess with them. And then just run it. One other note, you have to set the learning rate really small. Otherwise, you'll screw up the pre-trained model, right? Because I don't have that much data. If you take big steps, you're sort of going to put it out of whack. And you use just basic stochastic gradient descent. This is all the same. I should have refactored this to be shorter, but I didn't. Yeah, so then you say, okay, let's do 20 epochs, just fit the data, etc. Note that it's slow, right? Because now I'm training the whole big model, not just my top few layers, but messing with multiple layers and having to do computations through the whole thing, through the whole 20-something layer model, and doing backpropagation through all of that. But it gets you another 1 or 2%. Yeah, 2% or so. I need 2%-ish accuracy, whereas before it was about 90. So still, right? I mean, with 2,000 training images, and in, I don't know, an hour, even without GPUs, etc., I got something that would have been way, 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 way better than state of the art 6 years ago in the computer vision task. So this is something that you can definitely do for vision. Even if you have a small amount of data, dropout plus pre-trained models means you can get pretty good performance, right?
Those layers that you fix, could have also be computed up to this point.
Yes, it might have been faster. I'm not sure. You definitely could pre-compute because you don't. Yeah, you're not changing the weight, so you're going to have the same activations for all your images. Depending on how big your intermediate representations are, that might actually be slow. Mm-hmm. Yeah.
So then, if you then, let's say, like, pre-compute up to this point,
Yeah.
so that gives you like inputs to like the further model.
Yeah, so that's what I did up here, right? When I
drop the initial layers from the
yeah. I mean, that's basically what I did here, right? I mean, here I just split it into the original VGG layers and my own layers, but you can compute the bottleneck features and then just make a model, from those features to the outputs. So you could do that, right? You can compute through a certain layer in the model, somewhere in the middle, and then just delete those early layers and feed in the bottleneck features. Read the documentation for Keras. It's quite good if you're trying to do stuff like that, but it's actually pretty, well, yeah, the library is also quite good, right? You really pretty much can just go in and say, okay, I have my model.layers. If I just delete the first 10 of them, then I have the rest of them. Where was model.layers? Right here. So this is just an array or a list, and you can just get rid of some of them. Pretty much. You might need to adjust some parameters of the model to tell it that, okay, the input is now a different shape. But it's pretty straightforward to do that. That's kind of what I did in this second thing too, right? You can stack two models together. Yeah, so other things you can do, right, that I didn't do here, but if you wanted to get even better performance, you can play with parameters. Clearly, it's overfitting. So you could add more dropout or penalize the weights some other way. You could do more data augmentation to generate more fake data, etc. You can keep fine-tuning, perhaps.
I noticed that people don't usually now person these images don't use L1 regularizers, the one optimal.
You can, yeah.
But I don't see them that really using it. I know you can, but
people I think do. So L2 is pretty standard. In a lot of papers, we'll use L2. Dropout is more theoretically justified, and in the sense that there's no real reason a priori to believe that your weights need to be small. Like maybe there's a good reason for some of the weights to be big. And even if not, like why L2, why not L1 or 1.5 or something. Whereas dropout essentially is an ensemble method without having to make an ensemble. You're basically in the same space, making an ensemble of a lot of different networks with different topologies. And so people sort of understand why that works. It's both stronger and kind of more unbiased in some ways. So that's what I tend to default to just for playing around. In general, yeah, you would absolutely want to, try L2. And if you look at papers, it's pretty common. People say, we use regularization. We'll talk a little bit more about that tomorrow, though I'm not, a true expert at that. All right, so any questions so far? All right, so let's talk about a few more convolution things, and then we'll pause again, I think, before we switch gears to sequential data. So sometimes we're not just doing classification, right? So I might want to do, well, essentially object detection and then classification. So something like this, right? Figure out, okay, there's cars, pedestrians, trees, etc. And there's some cool ways to do that. Yeah, so how do we do that, right? How do we find bounding boxes and labels for objects in the scene? One thing you can do is just run your classifier in every subimage or in many subimages and see where it says, hey, I found a car. That's works, but it's incredibly slow. Another thing you can do, I guess that's the top thing here. There was this cool paper from a few years ago, and there's some updated work that's even cleverer that basically notices that if I'm using a convolutional network, then I'm already basically computing at every point, every region in the pixel, kind of all of these convolutions, right? If I just run my convolution from a classifier on the whole image, even if it's big, I'm going to have all the values at every point. And so then, if I only knew what bounding boxes to look at, I could use those values that I've already computed and just sort of do the last classification layers at each step. So that's basically what they end up doing, is they run the convolution on the whole image once. They have a separate sort of predictor to figure out where there are likely to be images based on the features that it computed from the convolutions. And then where it thinks there's probably going to be something, it's going to do a, kind of sliding window approach using the convolution features that are already pre-computed, running it through a classifier and saying, okay, right here, there's a bear. Over there, there's not a bear, a salmon or whatever. And so much faster, you can kind of do a parallel computation and get more or less all the objects in the image with their locations for roughly the same cost as just doing a single classification pass.
Do you think they change the window size?
They also change the window size, yeah.
So
But
they do all the bounding parts at the same time. This roundable window size in one shot.
so convolutions, right, don't care how big your image is. So you can run, like if you had that VGG network, right, you could run everything up until that last dense layer on the entire image, no matter how big it is. And then you can look at the values from any subregion and feed that into a dense layer that sort of has some fixed size. So basically, you can do all the hard, like all the expensive convolutions once, and then this simple thing you can do is then you can do a sliding window across those features of a certain size, or I think they do a couple of different sizes, right? They look for big things and small things, etc. And see where it gives you high probability classifications. What they actually do, again, is you can do a little bit more clever by building a little regressive classifier to say, given these features that I've computed from my convolutions, where are there likely to actually be things to look for, and only look in those places as opposed to everywhere.
I thought that the previous model, they all start with a fixed size.
Right. So
the input size is sort of fixed.
Right.
So in this problem,
The reason that it's fixed is because if at some point in your model you have something that's not a convolution, but you have a dense layer, it needs to have a fixed size input. Right? So if I have a network that's convolution, and then like, okay, I have 32 by 32 by 6,
yeah, so
and I'm going to go from that to my classification layer with a dense layer. Now I need something that is actually 32 by 32 by 6. Whereas if I run my convolutions on some other size image, I might get 42 by 42 by 6. So depth will be right, but the spatial dimensions could be different. And so what you do is you say, look, I'm going to run in the whole image, so maybe it'll get me something that's 120 by 120 by 6 in the last layer. And now I'm going to look at 32 by 32 windows and run my dense network forward just from that point. So a dense network is trained on some fixed size thing. Yeah. I guess, we can look at the paper for details. And again, there's a few other papers. Actually, Karpathy had a paper from last year that was an updated version of this, including labeling, not just labeling, including actual captioning, I think. But main takeaway is if you're trying to do boundbox detection, you can do it in clever ways using convolutions. You don't have to actually sort of, do a whole bunch of repeated computation. Okay, and so then you asked earlier what you can do besides vision with convolutions, right? And really the point is, the reason we can do convolutions is we have these assumptions, right? There's spatial invariance and there's locality. And if those make sense, then you can apply convolutions. So we already saw, MRI, so 3D imaging makes sense. Audio, there's a paper that does convolutional networks on the Fourier transform of audio. Again, you can sort of say, look, probably what's going on at this frequency and what's going on at some other frequency matters eventually, but I don't need to look at each individual point, right? I can sort of do local analysis and then build it up over time. So this is, I think, a 1D convolution in frequency. What do they do? And then dense layers at the end. You can read more about it if you want, Spotify thing. Video is another obvious place, right? So it's a little funny, well, not funny, but it's different, right? So you can do the same convolution stuff on the spatial part, but there's also the time dimension, which has similar assumptions, where again, right, you can probably figure out what's happening at each second and then put it together from that what's happening at a longer time scale, but it's no longer, forget what's the technical word, isotropic, right? Like the spatial dimensions and the time dimension are different, so you have to think about how you treat them separately. There's this cool data set that folks from Google and Stanford put together of a million YouTube clips of various sports things for people to develop. Yeah, try to figure out how to do video. There are some interesting challenges with video, mostly around just computational limitations, right? Video is huge, so people have tried a number of different tricks, like yeah, looking at really low resolution version at first to get a general sense, and then zoom in if necessary. There's yeah, people have done things that sort of look at just the center of the frame at low resolution, because usually that's where stuff is happening, etc. And yeah, I mentioned this warehouse thing briefly earlier. There's this blog post, yeah, NVIDIA blog, that was trying to figure out, you know, what path, in what order should I send a picker in a warehouse to go pick up objects, and for a new object that I have to get, like, whose list should I give it? Should I add it to? So they had an optimal version of this that gave you the right answer, but it was very slow. It took many seconds per you know, per query. And so what they did is said, hey, can we approximate this function somehow using a network? And yeah, so basically they looked at it and said, look, if these are the two aisles that I need to make a decision on, and here's my travel time, the function is fairly smooth, right? So kind of, if you're close, it's going to be have similar values. And so maybe the locality assumptions that we need make sense. So they ended up using actually convolutional networks to approximate this complicated function, and got something that was very, very close, and 1,000 times faster, which then let them do a much bigger search through, and pick the right thing to do. Yeah, so as a general thing, like, neural networks can be used for function approximation of various functions, and if your function, as a function of its inputs, has these locality assumptions approximately met, then convolutions may make sense.
I do not completely get a picture about this optimization of warehouse acoustic. What does this mean?
So, read the blog post for full details. The basic problem was, I have a bunch of workers, and they're going around my warehouse picking items that I need to ship to people. And so when a new order comes in and says, hey, someone wants shampoo, and I know that shampoo, is an aisle 7, like at that particular point, there's a question of, whose list do I add it to, and where in the list do I put it? Right, so it's sort of an optimization problem that says, okay, people are walking around, like, who's going to be, who's going to be penalized the least? Like, how's this most efficient? And yeah, so it's a standard kind of path planning problem. There's a way to solve it optimally or semi-optimally. That's slow. And they were trying to say, okay, I want to quickly answer the question, if I put this thing on this person's list, this location, like, how much is that going to increase their travel time? I think was the way they set it up. And it turned out that they could use a neural network to feed in, the parameters as like, okay, here's the object where it is, and try to get an estimate of the time. I forget the exact details because I read this, I don't know, 6 months ago or something.
This is not a classification problem. It's more like a regression.
It is a regression, yeah.
So we haven't covered regression.
Sure, I guess that's true. I mean, the basic idea is you just take off this. Yeah, well, Right. If you just take off the sigmoid at the end and just spit out a number that you don't squash into being between 0 and 1, that's regression.
Oh, that's the way to do regression.
Yeah. You need to define the appropriate loss, right? How much you want to penalize being off, quadratic, L2 or something. And yeah, you can do regression. Where do they do regression? I guess, yeah, at the very, very beginning, the sort of toy linear model was a regression, but that's not that interesting. But yeah, you just...
Because there are ways to use in the classification to do regression. For example, you can use decision tree to do regression. So it means you partition your space into different classification
right.
And then
so I mean, yeah, you could certainly do that as well, right? You could say, look, I'm going to just break it up into ranges, 0 to 1, 1 to 2, 3 to 4, and have each of those be a class. I don't have good intuition for when one or the other would make sense. I mean, I guess my general intuition is I would start with the simpler thing of just saying, look, just give me the number, run the weights to give me the number. And if the network is big enough and you have enough data, it'll get it right. If you train it long enough. That's enough assumptions. If that doesn't work, you might be able to get better performance if you just want approximate regression by doing binning or something. But here, I'm pretty sure they just directly predicted a number and tried to, approximate correctly. Yeah, so here was an interesting article in the New Yorker last fall, or no, I guess it was in April, earlier this year, on applications in medicine, or people are really trying to do this. And I thought it was interesting because it's both kind of straightforward application of what we just talked about, and at the same time, kind of not straightforward in terms of how to actually make this thing really work in a real application, right? So the application is looking at people's skin. There's some kind of weird colored shape thing, something going on. Is it dangerous, right? Is it cancer? Is it benign? Is it blank skin, et cetera? So we have lots of dermatologists trained on this for many years in medical school and residency. And they can just glance at something and say, yep, they're fine. We're like, nope, that's not fine. Off to the hospital you go. So 4-class classification, right? Several different types of cancers and benign. Basic input is just an image, maybe multiple images. Less basic input is also things like family history of cancer and your own history of cancer and skin problems and whatever else that you might want to somehow fold into this. So, would you use neural networks for this? Probably, right? Vision, we don't really know how to describe. Like the dermatologists, who've been trained on this for years, they can look at it and say cancer or not, but they don't have a good way to describe why. They have some features, but it's hard to explain. But at the same time, like, how do you add in those other stuff? And how do you get the right baseline for different populations of patients, age, skin color, et cetera? Ooh, more snacks?
Are we taking a break now?
No, in a couple minutes.
Okay.
So this is actually interesting. You are combining image and the other
potentially
categorical data.
Right. So the question is, if you're really trying to solve this problem, you need to figure out how to combine image data and categorical data and possibly other stuff. One approach, which is kind of theoretically nice, is just to feed everything into your neural network as a bunch of inputs and then hope it figures it out. Another approach, and probably where I would start, is just train a separate neural network classifier. Just give me a number, and then train a more traditional model, decision tree or whatever, regression or something, that says, okay, given that prediction, that's sort of generic, plus this other information I have, how do I combine it into a final thing? So you can do, you don't have to use neural network as the only thing in your solution, right? It could be a component that you then combine with other things using factors that you understand based on some theoretical basis, for example, and don't have tons of data on. Yeah, some of the other data, like they have lots of images to train on, relatively speaking, but only a fairly small fraction of them do they have real ground truth, like was this cancer. For many of the others, they have a dermatologist's opinion, which may or may not be right, etc. All right, so that's actually, I think, the last thing on convolutions. Right, so next is, okay, how about text and sequences in general?
Sorry, just
But I'm going to take a break.
So out of the couple of ways that you mentioned about going about it, you're combining image data with other features. Do you have a set, like, in practice, is there a go-to method for that, or is it kind of just depends on?
I mean, I think it just depends on, it's probably the best answer I can give. There are definitely plenty of places where people are trying to combine multiple different inputs, sometimes multiple images, sometimes images and other stuff. We'll see some examples with robotics tomorrow. Oftentimes what you do is you have your sort of convolutional network computing a bunch of stuff, and then after you did that, before, for example, you go into those dense layers, you just add in some other information at that point. And so you don't start with the input as like, here's 1,000,000 pixels and these 3 numbers. You compute some representation of the image that's useful, hopefully, with the convolutional network, and then you take that feature and then you add in your extra numbers, sort of from the side. So sometimes you can have multiple inputs at different points in the hierarchy. If you read, some of the more complex papers these days that are trying to combine various different modalities, et cetera, that tends to be how it works. I mean, essentially, inevitably, that's how it works, right? Either if it's inside the neural network, then you can try to train the whole thing all at once. Otherwise, you still have your neural network, and then you have, Victor decided to use linear regression, and he decided that the weight should be such and such and such, which you can still draw as a network. You're just not training all the weights kind of end to end. And I think it really depends on training data, right? If you have all of that data for all of your inputs, and you have a lot of data, yeah, just throw it in, and that's a good place to start. If it works, then you didn't have to spend a lot of hours doing feature engineering. If you only have the data sometimes, or if you just don't, or if you don't have much data, but you have strong opinions about how it should be incorporated, because you have some theoretical model, then you might be better off doing sort of more traditional manual stuff, with some simple experimentation on top of the output of the neural network. Other questions?
For images now, I don't know, last time I checked, there was like ResNet.
Yeah, I think there's something even newer now, but you can just Google, look at ImageNet
Right.
last
I'm
year.
just curious, like, so now, okay, so it's best for images right now, but do they have people also, do they now also use it for the same architecture for sound, other stuff? I don't know.
Right, so that's a good question, right? How do I pick an architecture? And would I use the same thing for sound? So short answer is no, right? I think for vision, if you're doing, if you start with ImageNet, if you're doing vision of sort of normal real-world images, you should absolutely use something similar to what does well in ImageNet. There are other considerations besides accuracy, like how complicated the model is, how slow it is. There are versions that are much smaller, maybe they're a little bit less accurate, but if you're planning to deploy on a phone, for example, power and space and performance become much more important often than an extra few % performance, or not, depends on what you're doing. So, but roughly speaking, you'd want to base something on ImageNet probably. If you're doing other vision stuff, right, medical imaging, ImageNet's still a reasonable place to start, but I would expect it to be less good at generalizing because it's sort of a different domain. Things look different visually. It may not be the same features that matter. I don't know if there are good pre-trained models for medical stuff because it's harder to get good data, but you could try. I would probably still start with ImageNet. Right? If you're doing sound, the parameters are all going to be different. One thing is 1D convolutions. Typically, at least if you go straight from the waveform. And yeah, now you have to know how many milliseconds at a time do I look at? So I would go look at the sound convolutions literature and see what people have done and start kind of there. Same for any other domain.
If you're trying to build a domain-specific solution, you may want to start with data from the domain. I mean, there was also talk about like, chatbots being trained with different corpuses, and one of the things is like the movie corpus, like the Cornell movie corpus. So the chatbots typically respond as though they've been trained on a Hollywood.
I'll be back.
And how many people talk in terms of it's the Hollywood dialogue, right? So it depends on what kind of domain you're training on. Generic ones probably make that kind of stuff, but if it's like domain specific, healthcare related, or detection of fatigue and flaws and metallurgical failures and things like that. So it has to be something specific to that particular domain.
These days, this stuff is so well studied. Well, not that we understand it, but so many people are excited about it that there's literature on pretty much any application, at least a little bit. And so I would start with that. And again, see kind of, okay, people got reasonable results with this kind of architecture. So probably start with something along those lines. That's one. And again, the other is sort of first principles. If you have some sense of what kind of ranges are important or how complicated are what features that probably matter, if you just play around with vision and audio as different complexities of problems, you'll begin to get some sense, right? Like if I'm doing something kind of like ImageNet, even in a different domain, you're talking tens of layers and relatively big convolutions. If you're doing small images, sort of simple things like characters, 3, 4, 5 layers, small convolutions, right? If I'm doing, I don't know, trying to figure out, I don't have really good intuition for audio, but still, like I have some intuition, right? Just phonemes matter, right? So I'm not going to look at 5 seconds at a time in my convolution. I might look at 100 milliseconds in the first layer. Maybe that's wrong. Maybe 500 is better, but it's not. It's not this big, and it's not 1 millisecond. There's going to be again a few layers. You need to pull out the frequencies, and you need to pull out sort of things that look kind of like phonemes. You need to put that into things that look kind of like words. You need to put that into things that look kind of sentences. But again, for audio, for standard sensory stuff, there's lots of literature. I think it's harder if you're doing something like, I don't know, 8 things that people don't publish about as much. Network log analysis, or even for finance. There's lots of people doing it, but I don't know how much they're being public with what they're doing. So it's going to be harder.
I have a question for the dropout. When you say 50% dropout, 25% dropout, do they do the random dropout, or they do the interlacing, or they have their own?
The normal model for dropout is, if I say 50% dropout, that means for each training example, I randomly get rid of, basically I keep each edge with probability 0.5. Keep each weight, each edge, with probability 0.5. Right. So if I have a network with 1,000 edges, for each one I randomly decide whether to keep it or not.
So
for each input.
So you have 1,000 edges, right? So you want to drop to 500 edges. So you simply randomly assign you want to keep this or not, something like that.
Yeah, exactly. And so usually it's not that you're going to exactly 500. It's really just for each one you randomly pick.
So so you create a probability, you create a random number, where 0.5.
Yeah. Exactly. Yeah. So you make a matrix of the same size as your weight matrix, and you threshold it at 0.5 or whatever it is, and then you get rid of everything that's.
So you need to run multiple times. Every time you drop out different edge.
Exactly. For each, ideally for each data element, you have a different dropout, and there's a little bit more. Basically, when you do that, you also have to renormalize the values. So if you get rid of half, and you multiply the other half by 2. So that your average stays the same. But yeah, I mean, the toolkits, etc., handle it for you to do that normalization.
Also, are you running the Keras? Are you running the standard Keras, or are you running Keras 2? Or?
I switched halfway through. So right now, what I'm using is Keras 2.
Okay, so either one works on your example, or you need to better switch to Keras 2?
I mean, I guess my suggestion is use Keras-2. That's what they're using going forward. It's the thing that works with the latest, TensorFlow 1.0 and up. In general, the example should work in both. I think there's a few places where so they renamed some of the function parameters, and the old ones still work. But I think in a few places I got rid of the warnings by making it new ones. And so then if you use the old Keras, it will actually complain. It's trivial to fix. It's things like, it used to say NB epochs, now it just says epochs. But just if you use Keras-2, it should work throughout.
And the DSX has Keras-2?
DSX, last I heard, did not have Keras-2 yet, but that was a few months ago. I haven't checked.
Yeah, I don't think we've updated that.
March, maybe. At some point you probably should, but it's it's not in TensorFlow as well. I think last I checked was before 0.1,
Right.
or before 1.0 rather.
And your TensorFlow is using basic TensorFlow or
I was using like 1.1, I think. Again, it shouldn't really matter. Well, Keras-2 only works with 1.0 and above, but beyond that, I don't think it really matters because we're not using any of the sort of complicated advanced features.
So should we take a quick?
Yeah, so let's take a break. I'm losing my voice. I'm going to stop the recording. People on the internet will be back in about 15 minutes at 4 p.m. Central Daylight Time. Whew, I'm going to lose my voice.